Okay, so
Are we still taking our final?
your final exam is scheduled, I believe, right when you. Is it right when you get back from Chinatown?
It's before spring break. So
It's after. It's that short week before spring break.
no, I just wasn't sure if we were doing it when we finished or like.
No, you guys still have.
Didn't last not get a final?
They had a final exam project, which I will tell you took many more hours.
Oh,
Okay,
Never mind.
I'm not sure what I'm going to do this year, so don't ask me yet.
I hate
We should make a movie just like the one we watched.
Yeah, sure.
All
right.
It takes time and effort.
It's already time.
1, 3. Okay, so I saw some of you got your packets out when I told you to like start working on this after the quiz, and everybody just kind of looked at it and
I got scared.
said, "Oh my word, I don't remember this stuff."
close.
Or like, "Oh yeah, I remember the rules. Like when you multiply them and you add the exponents, and when you divide, you subtract. Those are the rules." But what about
Graph.
just the graph
Oh,
and
yeah.
the domain range? Okay. So what does an exponential function look like, and why? It goes like, so it starts off slow, and then it increases exponentially.
Wow. What does
I
that mean?
know what does that mean?
You have a video about that?
I'm sure there's a video about that, but we don't have time right now. Okay. So what's that mean? Exponentially.
Oh, like it never stops.
Okay, so it increases, it never stops. What else?
It keeps getting greater faster as it goes.
Okay, and why is that? It has to do with where's the variable?
It's in the
In the exponent, okay?
What if it's negative or fraction?
Okay, so those would be, when we get down to that
We're gonna get to
topic, those would be those are a type of exponential function. We can have exponential growth, which I know you talked about, and exponential decay. Exponential decay would be if you had like 3 to the negative x. Well, what's 3 to the negative x? It's 1 over 3 to the x. Okay, we'll talk about that. Let's not worry about that. Let's just do a basic one. We're going to start with 2 to the x. Okay, domain. What can you plug in for x? Anything, right? There's
All
no
real
restriction. So all real numbers. However, the range. Okay, so let's just for now, if we've all forgotten, let me just make a little table. Okay, so you said we could plug in everything, right? We could plug in negative numbers, we could plug in 0, we could plug in positive numbers. Let's start with, let's just plug in -2, -1, 0, 1, and 2. Okay, so hold that thought. What does 2 to the -2 mean? Well, remember, a negative exponent means it's 1 over 2 to the second power, right? When we change something from the numerator to the denominator, or the other way around, it flips it, right? So that's 1/4. And what happens when we plug in -1? It just becomes 1 over 2. Are you okay with that? What's 2 to the 0 power?
1.
1, okay. And of course, 2 to the first. You can 2 to the first, 2. It's okay. And 2 to the second power is 4. Okay. Now think about those negative exponents for a minute. If I plugged in 2 to the -3, I would get 1, 8, 2 to the -4 would be 1, 16. Is it ever going to reach 0?
No.
No. So we have an asymptote here at the x-axis. So y equals 0. We're just going to, well, it's kind of hard to see on here, but I'll just kind of write horizontal asymptote y equals 0. And then let's go ahead and just plot these points. We have -2, 1/4. And then -1, 1/2, 0, 1, 1, 2, and 2, 4. So just by plotting those 4 points, we can get a pretty good idea of what the graph is going to look like. Okay. through the points, but imagine it did. Okay, so we said domain was all reals, and now bottom to top for range. So we already said it's not going to reach 0, so that means we're going to have parentheses 0, and we already said that it's never going to stop, right? So it's to infinity. Good? So, and back to us a little bit. Okay. What's the difference between this function and this one?
It moves the horizontal asymptote up 3.
Okay, so we've added 3, which basically would mean if we took all these y values, because that's essentially what we're doing, we're adding 3 to the y values, so that moves everything up 3. We don't need to plot all the points. Just go ahead and move the asymptote to y equals 3. And again, I'm not worried about a lot of details here in the graphs, just a sketch, so that we can talk about domain and range. Domain, anything change?
All real numbers.
All real numbers, so we're good with that.
Is that, why is there a way to like just look at it and know it's doing this?
Okay, so if there has been, so to find the y-intercept, all you need to do is plug in 0 here, right? So 2 to the 0 power would be 1, 1 plus 3, 4. Okay. And what about the range? It's just 3 comma infinity. We can't include 3, so we put parentheses around it. Questions? All right, so our rules for exponents. I heard this part we remembered, right? So a to the y times, or sorry, a to the x. So a to the x plus y over here to 2. Good. A to the x minus y. A to the xy. Okay, so the way we can, this is just kind of saying we can rewrite it so it's a times b to the x power. Or if you started with this, it's almost like distributing the exponent. And same thing here. So what happens when you have the quotient? You could just do a to the x over b to the x. Okay. That's okay. Here's maybe looking at a different part. Or, I don't know. Okay, example 2. Write the exponential expression to have the indicated base. Okay, so I have 81 to the 2x. I just want to rewrite that with a base of 3. So in other words, I want, so base 3, I want 3 to some power. Okay? So don't worry about the 2x for right now. Just look at the 81. So if I have 81, that's 3 to what power? 4. Okay. So if I have 81 to the 2x, right? So imagine 81 to the 2x would be 3 to the 4th power raised to the 2x power. Make sense? So you're just going to multiply those and we get, good. But the next one, so this one is 1 over 8 to the 1 minus x. We want to rewrite that so it has a base of 2. So let's look at, just don't worry about the 1 minus x, just look at the 1 over 8. So think about 1 over 8. Good, so you recognize in the denominator 8 is 2 to the 3rd power, so the reciprocal, right, would be 2 to the negative 3. So then if I have 1/8 to the 1 minus x, that means I have a 2 to the negative 3 to the 1 minus x power. Makes sense? And then go ahead and distribute. Who can give me the answer for that then? Go ahead, Jim.
Then do the 3x minus 2.
So he just rearranged the terms. That's fine. Okay, you could leave it as negative 3 plus 3x or rearrange. Good? Oh, yay, we get to use our calculators. So, yeah, so let's just do a quick review. How do you find, oh yeah, do your calculators. everybody have a calculator?
I
If not, just, and just, even though you will have a lot of non-calculator stuff, just make sure you bring it every day because we are going to use it very often. Okay. Oops. Didn't mean to do that. So, who can remind me in the class, how do we find the zeros?
Oh.
Okay, so, oops. Okay, so we're going to graph it. If ever your window gets kind of like maybe you had something zoomed in or you were in a certain format, everyone knows the zoom 6, right? Makes it -10 to 10, -10 to 10. We're good with that. Okay, you said second trace. We're going to use this button a lot this year because down here you'll see these are kind of funny symbols of dy dx is something that we'll use, and we'll use the integral. Okay. And we want to find what? We want to find the 0. Right, so left bound, we just want to make sure it's to the left of the point. Doesn't really matter where. And then, what's the key when you're choosing your left and right bounds? When looking for a 0? It's got to cross the x-axis, right? So you want to just make sure that one's below, one's above. And then the guess. The guess isn't really all that important unless you have multiple intersections or places that you're looking at or multiple graphs. I usually just press. If you have lots of stuff going on, just you can move the cursor so it's closer to the point you're looking for. That's all. So what do we have? 1 point. Okay, so I will tell you that we're going to go to 3 decimal places. So I'm going to explain later on in terms of the AP exam, and I think I mentioned this yesterday, you do not have to round, but you have to go to 3 places. Okay, so
That's the minimum. Like it is.
exactly. You never round to the 10th unless they specifically tell you. You never round to the 100th. You either round to the 1000th place or you truncate, which means you just stop at the 1000th place. So I will always be okay with you rounding. What do you get when you round? .262. And did it look different if I didn't round? Well, let's see. Yes. Right? 1.261. And now it seems weird to leave it like that. That is okay to write as an answer. Okay, just getting you in the habit of 3 decimal places, round, or just take what's on your calculator. Go ahead and find the next one. What do you get for that? I'll just... Okay, so 0.916. And is that the same if you don't bother rounding? Okay. And in that case, that's the only answer that you should have. All right. Any questions so far? Okay, so exponential growth and decay, we kind of briefly talked about. Exponential growth is when your base is greater than 1. Right? So we just looked on the previous page at y equals 2 to the x, so that could be like our example. Right. Exponential decay would be, what would be an example of an exponential? So just, oops. One half to the x still has a horizontal asymptote at 0. Right? I'm not going to bother with the asymptotes. Okay. Now we talked briefly also yesterday about what happens when there's a negative out in front. Do you remember what that translation is? What happens? It flips. Okay. So just a quick reminder with in terms of, where are my markers? So if this is y equals 2 to the x, what would y equals negative 2 to the x look like? Flips it across the x-axis.
So is that still exponential? No, it's different.
Well, yeah, k can be any constant, so it's a little complicated. Generally speaking, when we look at exponential growth and decay, we only look at positive coefficients. But these can still be referred to as exponential growth and decay. So when you have a negative out in front, that's usually thought of as saying a negative 1 times 2 to the x. So you're, oh.
Yeah.
Oh, okay, so that's still, don't worry about what.
Don't worry about the negative.
Yeah, I mean, that's why I just said, usually we refer, that's why it says right here, k is greater than 0. I'm never going to ask you if this is growth or decay. I'm only going to ask you if it's growth or decay if it's positive. It's still an exponential graph. It just doesn't represent growth and decay because growth and decay is only defined for positive values. And that's because of the real examples that we have too. I mean, it's something that you can actually apply. Whereas this has a different, that one can't be applied to growth and decay type problems. But we still have those graphs to deal with. So below, and we talked about what happens when there's a negative exponent, right? So if I have y equals 2 to the negative x, technically, because the negative is in the exponent, that would flip it with respect to the y-axis, but you also said that that was the same thing as 1/2 to the x, which we said was that. Right? Okay, so we have 4 graphs, A, B, C, D, and then take a look at right below that are 4 quizzes for the equations. Take a minute, see if you can match up which one is which. Okay. No, you are.
Oh.
I mean, not, you're right.
Oh, okay.
Not like
I don't know if I go that far, Jonathan. Not yet. I think you got to earn that.
You gotta get a 5.
When the x is negative, where does it flip over?
When the x is negative, that is going to be a y-axis reflection.
Yeah, I get to write it.
You got it? Let's see. All right. I would have said something. Goodness. All right, Jonathan wrote them in. Do you agree? CADB? Yeah? You sure? Any questions on any of them? So 3x to the minus 2 would just move it down 2. Right, this one. 3 to the x is like what we call the parent function. Right, that would be a negative, and a negative. So that's going to basically flip it across the x-axis and the y-axis, right? That's where d comes in, and then 1 over 3, that's the exponential decay. Good? All right. So we saw that really silly video yesterday about E and pi. Do you remember E? Or
Yeah.
approximately? Okay, so this is in honor of Euler, which we don't really get into Euler. What's that? Euler. Not Euler. Anyway, Euler. That's how you say it. Okay. You won't learn much about. We have something called Euler's method, but that's more a BC topic. So, but we do use E. We do use natural logarithms throughout calculus. So, let's talk about that.
Do we have to know f of x equals parentheses 1 plus 1 over x?
No, that's a BC topic. It's something called the harmonic series. Don't even worry about it. It's those of you that'll take BC next year, or if you go into Calc 2 in college, you'll learn about it. Isn't that exciting? Okay. All right, next. These formulas should look somewhat familiar. Maybe you've seen them in a different format or maybe some different letters. This one, I'm gonna just review very briefly. Have you seen this one? This is compounded when it's not compounded continuously. Like, let's say if it was compounded monthly, then okay. Continuously means it's continuously changing. Okay. Whereas, let's say you put money into a bank account and it's only compounded monthly. That means, okay, here's August. So what your account balance is August 5th is going to be the same as August 21st. And then August, right? It stays the same all month long. And then August 31st or whatever, or September 1st, you'll get the interest that accumulated during the month of August. And then all of September it'll stay the same. And then you'll get a new balance at the end of September.
So that's not continuous.
That's not continuous. Continuous would mean on August 5th, your balance is probably a little bit different. It just won't be much than August 21st. Okay. So K is the number of times it's compounded. So if I said monthly, then K is 12. If I said weekly, then 52. If I said yearly or annually, 1. If I said daily, 365. Good. Semi-annually? That's 6 months? Should be. Semi-annually is usually half a year. Two. It's okay. I won't ask you this. It's month. Usually I ask for monthly, daily, or yearly. Oh, sometimes I might use the word quarterly. Quarterly would be 4. Okay, A equals PE to the RT. I use this formula just when I talk about money because it's what it's for. It's just for money. And this, let me show you these two. Okay, so the one that I need you to know the most is this one right here. Y equals. Okay, so that's the initial value. Sometimes you might hear why not. Not meaning that's the first. Okay, so y equals y naught e to the kt, or y equals y sub 0 e to the kt. This is the one that you need to know more than anything. Right here. Okay. This is like big star, like make sure you know. Okay.
Is T in years always?
No, T is not necessarily in years. T is in years here because this is usually when we're talking about money and interest. So this is really important because we're going to get into some exponential growth later on in the year, like in chapter 6, for example. And T, so T can represent some growth in seconds, minutes, days, months. So, for example, did you talk about half-life a little bit?
Yeah.
Okay, so something like half-life could be, or the way that bacteria grows could be determined in days. So T is whatever unit of time you're working with. It doesn't have to be years. Okay, the money stuff is T is years. If you want, and it actually says that. It says years here, and it should say years in the one above. So again, Y, it says Y is amount after time T. That means that's like your final amount or your result. Right? So this is like the final result. Initial, this is what you start with. K is the rate. Well, that's that. Oh, time T. And if you want to just write time, doesn't have to be years. Okay. Good. All right. So let's take a look. Population in Lancaster, Pennsylvania.
Y equals 56,000.
Okay, so in 2000 it was 56,000, and it's increasing at the rate of 2.5% each year. All right, now make sure when you're using the rate here, when I refer to the rate, make sure you change it to a decimal. Okay, so here the rate of 2.5 would be 0.025. Good. So I have what? My initial, this is y sub 0. Right? So in 2000 it was this. What do you think it's going to be in 2020? That is just plug into the calculator.
What do you do with it if you have a decimal?
So population, I know it's going to sound strange, but we still go to 3 decimal places unless they say round to the nearest whole person.
Okay.
So, just get used to it. It's just one of those things where I know you're probably used to thinking, oh, it's population, I'm going to round to a whole person. If it says round to the nearest person, then you do that. Otherwise, you still go 3 decimal places. Okay? What do we get?
92328.
Is that
92328.391.
0.391? And did you have to round, or was that truncated? Good. All right. Approximately when will the population reach 75,000? So now we're saying what? Yeah, so this is our y. This is our result. Now this, even though I'm going to actually review in the next section, we have to use what?
Natural law. To solve.
Right. So whenever we have a variable in our exponent, we have to use some kind of logarithm to get that. Okay. So before we do that, we have to have e to that power by itself. So we got to get rid of the 56,000. So we're going to divide first. Right. And I know that reduces, but I'm going to leave it. Don't round parts of your answer when you're working with it. So for example, if you do 75,
I mean, when you show your work, you round it like on paper, but on the calculator still.
right, don't, okay, so when I round, so if I look at this, it's like 1.339. Don't round that while you're working with the problem. You guys know how to store decimals into your calculator? Okay. If not, just see me. Or just leave it like that. Just leave it as a fraction.
So if I get this right, like 2011, it's going to be a
Oh,
decimal.
approximately when? You could say, in a case like this, that would be okay. Yeah, I mean, you could say,
2012 or 2011?
yeah. I mean, that says approximately. You can even leave it as in t equals 11 point.
I can just leave it at that and that's fine.
That's fine. Yeah. Okay, so then we said ln, right? So if I do ln,
But on paper, can you round? Like, will you get marked down if you round on paper, but like on the calculator, you keep
that's okay. So if you're writing it on paper, so you'll notice what I'm doing. I don't even bother putting that part in. That's fine. If you want to put 1.339, just as long, and on the AP exam, the same. Like, you'll get used to a lot of this stuff, kind of how you do things on the AP exam as we're going through the class. You can put 1.339. That's fine, as long as you use the unrounded version to get your answer for T.
Why does 75,000 equal 56,000?
Oh,
I see. That's the equation. That's the whole equation.
Yeah.
At the top.
Oh, yeah, I just plugged everything into the equation. All right, so we take that, we divide by, oops. Everybody get the answer?
Yeah, I got 11.685.
Okay, so T equals 11.685. Okay, that's fine. You can just leave it like that. Approximately when, you could say in 11.685 years. Yeah.
So you need to label for population too.
At this point, I mean, because I said estimate the population, you could say you could say like approximately this many people. I don't know. It's okay. I'm not going to worry about it in chapter 1. Okay. How are we doing? Some of this coming back to us a little bit. Not so bad. How much time is required for an investment to triple if the interest is earned at the rate of 5% compounded monthly? And then we want to compare it continuously. So there's actually two separate problems here. What was the formula again? So we'll do monthly here. And then we'll compare to continuously.
Is the initial amount 0?
Okay, so what's the initial amount? So it doesn't matter. Let's say, I'll write this on the board. Let's say you started with $100, right? And you wanted to triple it. So that means you have this. And then you have what's in parentheses. What happens when you divide
Oh,
it?
gotcha.
You get 3. What if you started with 3,000, or sorry, started with 1,000, ended up 3,000? When you divide, you're still going to get 3. It's kind of like saying,
Can you make it like a simple number, even like 1
well,
and 3?
it's so this is our formula, right? Let me just rewrite it here. So the no.
Or tomorrow, Monday, for the quiz?
No, you will never have to memorize this formula. This continuously you do have to memorize because it's used over and over. I'm not going to make you memorize this. In fact, I'm probably not even going to quiz you on this. I just have it there, just as review because you might see it somewhere else. But so you see, whatever my principal amount is, I just want to make sure I end up with 3 times that amount. So what happens when you divide by p? They just cancel. So you're just left with. So I have 3 equals, it was 1 plus 0.05, and it said monthly, so that's 12. Right, to the 12t. Good. Now, this one isn't quite so nice as the last problem because it doesn't have a base of p. It has a base of 1 plus 0.05 divided by 12, which is something. And I think it doesn't. Oops. Oh, monthly. Okay, T is years, but K is the number of times it's been compounded. So since it's compounded monthly.
Oh yeah,
Okay.
for continuously, can you use A equals PRT or Y equals, doesn't matter. Or Y equals Y. It doesn't matter which one equation you use, I'm
No,
saying.
they're the same. Just one's for money.
So
A equals PE to the RT is for money.
So it does matter. It's money problem. We use we only use that.
Okay, so Y equals Y sub 0 e to the KT can be used for everything.
Oh,
Whereas A equals PE to the RT is that formula, but just applied to money. They're identical formulas. It's just different ways to. I'm just.
this can be Y, this can be Y, easy. R can be K.
Everybody okay with that, or still a little? If you're more comfortable using A equals PE to the RT for all of the continuously, that's fine. It's just, I'm going to use the Y equals.
Why do we need
Y
that?
sub
Oh,
0.
right.
Okay, so
Because it's
I still got to, what did I say earlier? I said that you have to use a logarithm to get the variable out of the exponent. We don't have e involved here, but we still have a variable in the exponent. So I have to figure out a way to get that out. You could use a common log, that's fine. We almost never use common logs in calculus. We almost always, everything works with natural log, but that will work in this case. So I'm going to move the 12t to the front. Right? And then I want to isolate t, so I'm going to divide by what?
well,
Yeah, and you know what? I could divide by the 12 also at the same time. It's just, you have to be careful when you plug it into your calculator that you have to put parentheses around that so that when you type it into your calculator, you put ln3 divided by parentheses because you want to divide by both 12 and this. Does that make sense? So I'm going to take ln3 divided by and what do we get? Like 22.0 0.018 or 22.017. If you truncate, if you don't round, again, either answer is fine as long as you go to 3. Okay, so on the calculator. Oh, well, on the right side, I just wrote it that way just to cancel. Okay, hold on. So I have ln 3. And then I divide by 12, ln, and then whatever that was. Oh, that was 1 plus 0.05 divided by 12. There you go. All right. Question. All right, how about the continuously? So you can truncate, which means stop right there at the 7, or you can round because this is a 9, that would make it an 8. So both answers are equally correct in terms of the AP exam. Okay. I know it feels weird to leave that 7 because the 9's right after it. I'm telling you, it's still okay. It's fine. No, it shouldn't be. Try the continuously. Does somebody have the continuously done? Not yet? Anybody want to write it? Do you feel brave enough to write it, and then we'll write the answer? Is it right? Then I can help. Everything looks right the way you have it set up. Oh, I know.
I got 21.9.
1 plus 0.05 divided by 12.
This thing is so weird to use.
Did you put it in as 0.05 divided by 12?
Do we have to, like, when we plug that? Magic. When we plug that in, do we have to put in a 1 plus?
Or if you had it stored previously. So like when I did it on my calculator right here, it was my previous answer, so I just did answer. Or store it as like...
Oh, so it's not 1.00. It's like the whole...
No, that's why I said when you work within the problem, even though I put 1.004 here, I didn't actually use 1.004. I used the whole decimal that I had in my calculator because it's going to give you a more accurate answer. Oh, this one look good so far?
Whoa.
That one's a little easier. So when you have E, it does make it, it's a lot easier that you don't have to deal with this kind of messy stuff. You just have ln of something divided by the decimals. So good, 21.972.
Yeah.
All right, so which one's better?
Continuously.
Continuously. Because this, you triple your money in less time. Not much. And it's easier to do. Okay. Any other questions so far?
How are you?
I'm doing great. We're doing math.
Oh, God.
How could it? Oh, 21 or 21.972. And we still have 1.5 to do. Now we actually did a little bit of this already. So
Yes, please.
you have a test
Wednesday?
a week from Monday, I think it is.
Oh, yes.
A week from. Oh.
Yeah, the following Monday is Labor Day.
Wait, Monday is Labor Day. We don't have Small Monday.
Okay. This coming Monday is the 24th. The following Monday is the 31st, our test day. The following Monday is Labor Day.
Math is following weekend.
Okay. All right. What do we have here? Oh, it's only 2 pages. We can do 2 pages. Yeah, we can. Don't you love how we're covering exponential functions and logarithms in less than an hour? And you probably spent weeks and weeks on it. I'm probably in Algebra 2 also. And here we're just going to sum it up in an hour. Okay.
Oh, that's been 6.
Oh, that doesn't look good. Okay. It's all good. I got it. Functions and logarithms. All right, so we actually talked a little bit about functions before, but so we briefly talked about how do we tell if it's a function.
Vertical line test or same X.
Right, so we look for, does it pass the vertical line test? So that's just telling us if it's a function. Now, when we get into horizontal line tests, this tells us if that function is going to have an inverse function. So a function can have an inverse. That's fine. So like, for example, y equals x squared. That has an inverse, but the inverse is not a function. Think about, okay, so y equals x squared. It passes the vertical line test, but it doesn't pass the horizontal line test, right? So the inverse of that would be like a sideways parabola, and then that wouldn't pass the vertical line test. Does that make sense? It's kind of reverse. So we call that, when it does pass the horizontal line test, 1-to-1. So here's an example, y equals x to the third. That is a function that passes the vertical line test and the horizontal. So it has an inverse function. Okay. Something, maybe. A little bit. Okay. We'll get there. This one hits two places, so as I was just saying earlier, this is not 1-to-1. Okay, so this one, we'll just kind of say here, this one has an inverse function. Okay. Determine whether the function is 1-to-1. But use graphing calculators if necessary, because sometimes we forget what these look like. Hopefully this one, we know what that looks like. So square root of x. Is that 1-to-1? Does it meet the horizontal line test?
Yeah.
Yes. Okay, x equals, y equals x to the 1/3. What's another way that we could write that? Cube root of x. So that looks like this, if we've forgotten, like the s, right? Does that pass? That's 1-to-1. The cube root? Yeah. Okay, so that is its own parent function. How about y equals x to the third? We just did that, and actually these two are inverses of each other. Okay? Oops, my computer froze.
Oh, is this the thing where it's like the S curve to the top of that problem?
Okay, inverses are reflections in the line y equals x. We'll get to that, but that's where you flip it. You actually have to flip it that way. Yeah. Okay, my computer froze for the moment, but right below there I talk more about inverses, so we can look at that. We know that f of f inverse should be equal to x, and the inverse of f of x should also give us x. Like when you plug one in for the other, didn't you ever have to verify inverses? You didn't do that
I
much?
know, but I forgot.
We forgot. Well, that's why we're reviewing. No, that's to find the inverse, which we are going to switch x and y. That's right here. So when you want to find the inverse of something, you're going to switch the places of x and y. You're going to solve for y in terms of x, and whatever you end up with, that is your inverse. Now, some books, including our calculus book, does it different. They say solve for x, and then switch x and y. They're both correct. Okay, some people switch x and y at the beginning, and some do it at the end. Did you always switch right at the beginning? Yeah. Then I would say just keep doing that, because that's how I do it. So before I do that, let me just rewrite. So I have a y. You could probably combine this step and the next step at once. Now I'm going to put x equals negative 2y plus 4. So I want to solve for y.
So y equals negative x.
Isn't it already?
you switched it.
Oh, it switched it.